Good morning or good afternoon, everybody. It's my pleasure to be here. First, let me thank Giovanni and all your collaborators for this organization of this Training Magnetism Conference. And today, I want to show you some of our recent experimental results, where we show the giant cell production of spin current and cell spin orbitor in ferrimagnetic materials. In this particular case, I will show you with the gallium iron cobalt amorphous ferromagnetic and interfacing with copper layer. So in the first part, I will show the cell production of spin current that is like 25 times more efficiency than in the case of similar structure where we replace platinum instead of gallium iron cobalt. And then I will discuss some conditions to get the cell spin orbitor when we have the right symmetry for this cell production of spin current in the magnetic materials, and we have the condition of the good spin layer to absorb the spin current emitted from the magnetic layer. So one of our motivation is, besides fundamental research, is to face this exponential data growth challenge that we have, for example, to store the data. So we need faster and more efficient way to store and operate with data. And thanks to this property of electron and spin and different stimulus or interaction, we can face this challenge with new kinds of new type of memory. I will focus on this part on the spin orbit effect, but first let's recall the classical spintronics, where we exploit not only the charge but also the spin of the electron, and where we have the giant magnetoresistance effect and tunnel magnetoresistance effect. And in this case, we have a magnetic tunnel junction where we have two magnetic layers which are either 0 or 1, and they are parallel or anti-parallel. Their magnetization, they have magnetization parallel or anti-parallel. And this is a solution with this architecture for some kind of memory or magnetic memory, the MRAM. But there is some issues like limited scalability. And so thanks to theories like spin transfer torque, where we apply current perpendicular to this pillar or tunnel junction, then we can switch the magnetization of the free layer. Still, we have similar issues of thermal stability, and in order to increase the density of the memory, we can change from planar magnetization to perpendicular magnetization. But the question remains open, so in order to have a smaller, faster, and more efficient way to store and operate with data, new FS could provide that, and we believe so. And that I come to that some of us call spintronic 2.0 of a spin orbitronics, where the main operation is the spin charge current interconversion. So one way of this is thanks to spin orbit effect. So we can create, manipulate, or detect this spin current by different ways, but at some point in our system, at some place, we will need either interface or a layer with a strong spin orbit coupling. And in bulk material, this spin charge current interconversion is called the spin Hall effect, and in surface on interface is called the Edelstein effect. I will not discuss about this that's happening in Rashba or in metallic oxides of topological insulator. Here are a few references. It is not exhaustive. Also, there is nice review that I want to discuss today is in the bulk effect, the spin Hall effect first, and this happens in a magnetic material with a strong spin orbit coupling. So if we inject a charge current, we create a transversal spin current that is electron with opposite spin moving in opposite direction. The efficiency of this interconversion is called the spin Hall angle, and it's a dimensionless parameter, and it's the ratio of the spin current density we produce due to the charge current density we inject. There are, in our community, we have studied many materials. One of the mass study is the platinum. Along with my coworker, we have contributed with some material shown here in orange or in green. And thanks to this pioneer work of Mihai Miron and coworkers in 2011 and in Cefalù in Cornell in 2012, And now we know that when we sweep in plane current, we may switch the perpendicular magnetization of the attached magnetic layer instead of sweeping perpendicular field. And that is that we know now that the spin orbital. And because we have it's driven by the spin orbit effect of this material, the platinum in this figure. Once again, with my co-worker, we have contributed with some studies, for example, in platinum cobalt nickel multilayers, and more recently tungsten cobalt terbium that I will show in the next slides. And then we can develop new architecture for for magnetic memories, so-called three-terminal spin orbiter MRAM, where we take advantage of this strong spin orbit coupling of the bottom layer here to switch the free layer and this magnetic tunnel junction, the magnetization of the free layer. So that's what's interesting is that they found that the switching is very fast, so below 1 nanosecond. This is really very appealing for application. Even more recently here, at Lamour Institute in Nancy, in a study led by John Gorchon, we have shown that via photo switcher, we can switch the perpendicular magnetization with just a few picoseconds. Let me show you one example of the spin orbital with the ferrimagnetic material here. So we exploit the spin Hall effect on tungsten and in this three layer. In the left, we have the field-induced switching. That is, classical or standard magnetization manipulation with perpendicular field. So in this case, the sample is terbium rich. In the bottom, the sample is cobalt rich. A ferrimagnetic material, we have two magnetic lattice coupled antiferromagnetic. And something that we observe here is the opposite switching polarity. Here in the right, in the middle in the right, we have the spin orbital experiment of the switching with current. So instead of sweeping perpendicular field, we sweep in plane current and we reverse the perpendicular magnetization of the cobalt terbium ferrimagnet. So we can see here that this is the 100% magnetization switching. They change when we change the little in plane field. We can switch even with the very little in plane field down to 2 millitesla. But something that is unexpected here is in this case of the terbium rich. You can see here, this and this have the same switching polarity. And here is expected the opposite way, like here. And what is that? Independently with have performed other experiment. I will not show today here, but it is here in this reference. And then we show that actually when we have this sweeping current experiment, we heat up the sample, this device, above the magnetic compensation temperature. So it means that in this experiment, the device is no longer terbium rich, but cobalt rich. And that's because here and here we have the same switching polarity. We further perform temperature dependence, and very interesting, we found out that the switching happened when the device reached the same temperature, independently of the initial temperature. So we call this characteristic temperature a switching temperature, as it shows here, a function of composition of cobalt in this cobalt terbium ferrimagnet alloy, and this increase with cobalt concentration as the Curie temperature also increase, and opposite that the magnetic compensation temperature, which decrease when we increase the cobalt concentration. Also, I'm not showing here, but angular compensation temperature also decrease when we increase the cobalt concentration. So this is from the experimental side of our results. From the theoretical side, let's remember first in the rare earth transition metal alloys, and we have several characteristic temperatures that I already mentioned, and that's because we have two magnetic lattices, antiferromagnetic coupled, but not compensate, and because the behavior with temperature of each magnetic lattice is different, as schematized here in green for the rare earth and in red for the transition metal. So we have a temperature where net magnetization vanish. This is the magnetic compensation temperature, where the angular moment vanish. This is the angular temperature compensation, and when the sample is no longer magnetic, this is the Curie temperature. But recently there is this theoretical paper where they mentioned that in rare transition metal alloys, they have also cell production of spin current driven by magnons or thermal magnons, and this vanished at this temperature. So I just pick up this this condition as also a characteristic temperature. So now, I mean, this is from the theoretical point of view, but I'm not totally sure if this is the same or is related with this switching temperature that we reported here experimentally. We need to do this temperature dependence on magnetization in our same samples, but it's not quite easy, as I believe at the beginning, because the magnetic signal of ferrimagnet are weak, and a few nanometers even much weaker. So there is, I mean, a challenge that we were facing in order to relate these two characteristic temperatures. So that was just an example where we show the spin orbitor by external spin Hall effect, in this case tungsten, or to switch the perpendicular magnetization of cobalt terbium. Now I come to the main part of my talk, where I want to show you the giant cell production in this gallium iron cobalt copper system. So let's recall again the spin Hall effect symmetry. So this happens not only in heavy metal, but also in magnetic materials. When we inject a sharp current, we produce a transversal spin current with this spin polarization sigma. The symmetry here is that this sigma is perpendicular to both, to the sharp current injected and to the spin current produced, and the efficiency is called the spin Hall angle. But there is also this other symmetry as reported here in this theoretical paper. And in this case, in a magnetic material, in addition, we have a spin current where this spin polarization is parallel to the magnetization of the magnetic material. And the efficiency of this interconversion we call the spin anomalous Hall angle, following the nomenclature reported in this study. In our community, in the last year have been many progress on both sides, experimentally and theoretically. Here a few studies, is not exhaustive, but we can summarize all this as we have done here in our recent publication, with the spin current from magnetic material having two symmetry. One that we call it the spin Hall effect lie, where the spin polarization is perpendicular to the magnetization of the magnetic material, and the spin anomalous Hall effect lie, where the spin polarization is parallel to the magnetization of the magnetic material. And so we can straightforward see that this condition of this symmetry cannot produce cell torque on its own magnetization because they are both parallel. So we can summarize this here. We have this symmetry of cell production of spin current, the spin anomalous Hall effect. So this cannot exert cell torque, no way, because they are parallel. And the other symmetry that we call a spin Hall effect, in this case, we may produce a cell torque, but the condition is that the spin current emitted from this magnetic or ferrimagnetic material is absorbed outside. And for that, the condition is to have a good spin sink layer. Well, experimentally also in the community have been shown actually the switching of single magnetic layer, but different explanations have been done for that. For example, here in iron platinum have been shown, I don't know what is the coupling layer here, on top of this bottom layer, or just on top of oxide substrate here. Also in cobalt terbium, between these two nitrous silicon, that is very, I mean, interesting, but I still don't understand all what is driving this switching here, because there is no, as the author report here, there is no gradient composition. And in our case, we have tried like 5-6 years ago in single cobalt terbium different thickness, and we observe no switching in single cobalt terbium layer. But of course, the material here are different, directly on silicon oxide substrate, and the capping was aluminum oxide. And here all other studies where they don't report the switching by sizable damping light and field light torque by second harmonic method. And here in the case of permalloy, a few examples, either by care, spin torque FMR, or spin pumping and temperature dependence, this study in Grenoble. So that I want to show you is that if we have a good or large cell spin current production in a magnetic material, and if we have this condition, we may enhance the cell torque from the magnetic layer. So before to show that, I want to show the large efficiency in this gallium iron cobalt. And the technical choice was based in ferromagnetic resonance, this spin torque ferromagnetic resonance method. This is a picture of our setup in Lamour Institute in Nancy. And here a schematic. We have our device here. We use radio frequency between 2 and 40 gigahertz with locking detection. But in addition to this gigahertz current that we inject here, we will add a DC bias current to modulate the language of our fMR signal. And this is not exhaustive, just a few examples of this technique. And actually, here in Nancy, we already report some study using this method. For example, in using flexible substrate here, or you studying a high-quality epitaxial iron platinum system, or in this case, nickel iron and iridium manganese antiferromagnet. Here is our main system, 3-layer, and we have nickel iron or permalloy on top of copper, gallium iron, cobalt. The signals are 4 nanometers of permalloy, 6 of copper, and 10 nanometers of gallium iron cobalt. And we can see here 2 ferromagnetic resonance line. Low field correspond to permalloy, and higher field correspond to gallium iron cobalt. This is for 10 gigahertz. And this is not difficult to identify each one, because either the position of the value of the resonance field and also the line width. We can see here that this line width is much higher than this. When we have the nickel iron resonance, the oyster field or radio frequency field generated by the current flowing in copper, the AC current flowing in copper and gallium iron cobalt will may precede the magnetization of permalloy when we reach the resonance condition. And in the case of this signal, is the other way around. Now the oyster field generated by the current flow in permalloy and copper, this is the extent here by this radio frequency field. As we sweep the DC field, and when we reach the resonance condition, we may precede the magnetization of the gallium iron cobalt layer. So we can identify both, and we can do, for example, other experiments like frequency dependence. Just to mention, most of this experiment was performed with David Céspedes, my former interview student. And here in the frequency dependence, we can see, for example, the typical square root behavior for permalloy. That means that the plane of the sample is an easy plane for magnetic anisotropy. However, here in orange, you can see a linear behavior, and when the DC field is applied in plane, so it means that the field plane is a hard plane for magnetization for gallium iron cobalt. So the easy axis for gallium iron cobalt is perpendicular to the interface. Moreover, we can also quantify the damping constant from this line width versus frequency. This is from gallium iron cobalt, much longer, much higher than the case of nickel iron. But our main experiment is to quantify the charge spin current conversion here. There is different ways based on this STFMR technique, like light chain analysis of a study of symmetry amplitude. But one of the more reliable is the damping modulation. This means that in addition to the AC current, if we add a DC bias current, and we study the variation of the line width as function of this current, we can quantify this charge spin current conversion. And let me show first an example on this control system, copper nickel iron bilayer. So here in the top, we see all the STFMR spectrum between 2 and 25 gigahertz. But for example, if we look at the case of 8 or 10 gigahertz, now when we add a DC current, we can see that there is no sizable variation of the line width of this signal. So as expected, no modulation of line width in nickel iron copper, so no charge spin current conversion, no the spin orbit torque. Now I summarize our main results. Here we have gallium iron cobalt copper permalloy, and we have a nice clear modulation of nickel iron line width with this DC bias current. If we quantify with a large value, in order to check this, we measure different devices or different samples. In this case, here's the spacer copper have 6 nanometers of thickness, and again we observe nice modulation of nickel iron line with, and even more, in order to make sure of these results, we have grown this 3-layer, where instead of gadolinium iron cobalt, now we have platinum. And we observe again this nice variation of the line width as function of current. But this is much smaller than this system. After quantification, we can get only 3% to compare again the 70 of 80%. So gadolinium iron cobalt is about 25 times more efficiency than this sample where we have platinum. So that is, I mean, very high value, and actually it's not surprising because in gadolinium iron cobalt we have a strong spin-orbit coupling by the 5D band of gadolinium. So now this value is really high. As I say, we have dosimetry, the spin anomaly Hall effect, and the spin Hall effect in this experiment. The question that rises are all come from BAL, or there is some interface contribution. Actually, there is some Rashba interface here. Was shown a few years ago that gadolinium and gadolinium oxide exhibit a magnetic Rashba interface. So with that in mind, and also we want to disentangle this value, and for that I come to the second part of my talk. So I show you already a very large efficiency for cell production of spin current in the system, much larger than platinum. And now, how can we evidence this cell torque? And now the technical choice for that is the second harmonic, quite well known in our community also. So we in a whole bar device now, you inject a current here, and we measure the transversal voltage in this whole voltage. At the fundamental frequency, we have a parabolic behavior close to zero field, and we have a linear behavior in the second harmonic frequency in this damping-like configuration or in this field-like configuration. And we can estimate the effective field who drive the spin orbitor. We have this condition, low field and planar Hall effect much smaller than anomalous Hall effect, and we have checked this in our sample. I will not enter in detail of this. This is law, of course, are very weak because it's only gadolinium iron cobalt copper. But I will summarize here our studies. So in orange is the bilayer with only copper, because we have now the condition of spin current absorbed outside. This is very weak. And when we have tantalum, we can see that it's also small but change the sign. However, when we have a platinum here in this 3-layer, gadolinium iron cobalt copper platinum, the damping line increase strongly. So this is because we say that we have, in addition of the cell torque coming from gadolinium iron cobalt, we have the spin Hall effect of platinum in the case of this 3-layer, and we have the subtraction of the cell torque of gadolinium iron cobalt and the spin Hall effect of tantalum in the case of this 3-layer. I will focus in the case of platinum. I mean, there is different ways where we can compute the cell torque of gadolinium iron cobalt, combining these two results, but I will use only the case of platinum because we know the spin Hall effect also in our platinum layer. So for that, let's rewrite here this condition. So the total damping line in this 3-layer is the addition of the cell torque plus the contribution of the spin Hall effect of platinum. And because we know the spin Hall effect of platinum, we can compute this damping line field coming from the spin Hall effect of platinum. This is the total. We make the subtraction, and we get the cell torque contribution of gadolinium iron cobalt when we have a platinum spin sim layer. And let's remember that this is only a spin Hall effect like contribution in this experiment for the cell torque, as I say in the first part of my talk. So even more, we can compute the spin Hall effect in this gadolinium iron cobalt, and it's about 16%. It's quite large, and this value is also large, comparable with the strong spin orbit coupling material used at room temperature. So these are the way we have evidence the cell torque in this gadolinium iron cobalt copper. Just quickly, let me show another signature that we can explore in the cell torque is the temperature dependence. in these ferrimagnetic alloys. So at 300 Kelvin, we are below the magnetic compensation temperature for this concentration, and at 340, we are above the magnetic compensation temperature. So that means that here in this gadolinium dominant phase, we have this fundamental harmonic signal. In the middle, we have the free light voltage, and then we can see is that the slope of this field light changes signs. That means that the effective field changes signs. I'll show here. On the other hand, here in the bottom, we have the signal of the damping light, and there is no change on the slope in this second harmonic signal for the damping light configuration. And that also means that this effective damping light changes sign. So, and this is a totally different signature from that we know in the community from the external spin orbital or spin Hall effect. So in our case, we have verified this with our own measurement in bilayer, for example, platinum, gadolinium, iron, cobalt, or other bilayer where we have a spin Hall effect, and we observe the same, the same sign here, no change. And this is, we can exploit this or use as another feature, another signature of this cell Tor in the temperature dependence will be similar in dependence with the composition. Actually, we are getting more results and we are checking more and more this. So with that, I almost finished. And before to come to the summary of my talk, let me acknowledge all the teams, all the groups we have collaborated. This nice collaboration here, particularly Professor Albert Fair and our younger students, David, Aldo, and Eloise Damas. She just started her PhD under the supervision of Sebastian Petit, Watlow, and myself. So with that, I come to the end of my talk. So I have shown you that we have a giant effective overall spin anomaly Hall effect plus spin Hall angle in this gadolinium iron cobalt copper system. And even more, we were able to disentangle combining damping modulation and second harmonic technique to disentangle the symmetry of this charter spin current conversion. And we showed the condition to enhance the cell Tor by getting a good spin layer or adding a good spin layer on top of this magnetic layer of this system. And also I show you even quickly another signature of the cell Tor in temperature dependence in the case of ferrimagnet, where we can change from gadolinium rich to cobalt iron rich. And as a perspective, of course, we were working on the switching with of external heavy metal. That's the cell Tor having this condition, and we're getting nice results also for them high production, scarmion motion. And this is I think he will show this, what actually we're showing that, open room to new system or to new architecture for this kind of memory of magnetic memories. And not only in this, I show here only with ferrimagnet, but we can see in other magnetic material with a strong spin orbit coupling, for example, some other alloys. With that, I finish. Thank you very much for your attention.